Hello, welcome back. So far we have been looking at the angular motion of a rigid body as it undergoes pure translation. That's very good. We have new tools, but we are not done yet with pure rotation yet. The next thing we want to do, and remember this was the goal from the beginning, that we want to find the motion or kinematics of any arbitrary point, like a point P, on a body, given some information about some movement of the body in general. So here the setup is that the body is undergoing pure rotation about this fixed axis, and I have a point somewhere inside or on the body. Location doesn't matter. It is important it is an arbitrary point. And because the body is undergoing pure rotation, point P travels around a circle. So if I look, this is me looking in the from top down in the opposite direction of angular velocity. What I see, let's draw it as solid. That this point P is moving around this circle that has a fixed center. How do we find the kinematics of point P? That is our goal. Define kinematics of P. And well, let's begin. What can we do? We have, let's simplify the problem for ourselves. We have a point undergoing, goes around the circle. We know how fast it is traveling, at least in an angular domain. And we want to find its linear velocity and position and all of that. A point undergoing circular motion is very well suited for what we have already studied a lot. Point P is a particle. We want to find its motion. And because it is going around the circle, we know the path, we know some angle. You can either use normal tangential frame or polar frame to find its kinematics. Both are almost equivalent. So let me define, some random reference. This is angle theta. Let's take this point O to be fixed. The position of point P, let me start writing it here. Position is vector R. Well, it's really, there's not much to define. I'm going to write this in a polar frame. So this is my UR. This is my U theta. And position, I can define it using polar frame notation. The distance from the center is all you need, and the angle. So that is easy. The next is velocity. That one is a bit more involved, but we can do it. Point P goes around the circle. Velocity always tangent to the path. So velocity, what did I do? Velocity is a vector tangent to the path, essentially along U theta. And in polar frame, if you remember, V was, in general, it was R theta dot, what was it, U theta plus R dot UR. And because we are dealing with a rigid body and rotation about fixed axis, this doesn't change. So your velocity is R theta dot U theta, or we have a new name for it, R omega U theta. You know its direction, you know its magnitude, very well defined. What I want to emphasize here is that the magnitude of it is R omega, R theta dot. And we always know velocity is tangent to the path, and we are in a very good position to have everything defined. But there's actually one other thing I want to say. In general, this U theta is a little clunky to work with, because as the body rotates, theta changes. We need to keep track of where U theta is. And sometimes it gets a little inconvenient to do that. The question is there a better way? And the answer is yes. A couple of observations. Note that because you're going around the circle, V is tangent to the path, and tangent to the path is perpendicular to your diagonal. So V is always, little r, is perpendicular to your position vector, the way in this particular case of rotating about a fixed axis. And also V, looking at, let me draw it color coded. This is V and this is R. This is 90 degrees. But also note that V is in the plane, inside the plane that is perpendicular to the axis of rotation. So V is also perpendicular to your vector omega. So now you have a vector, and let me write it here again. V, norm of V is R omega. You have a vector. Its norm is the multiplication of norms of two vectors, and your vector is also perpendicular to both of those vectors. And that means V is actually a cross product of these two. Remember, with cross product, if two vectors are cross produced, the resulting one is perpendicular to both, and the magnitude is magnitude of the first times magnitude of the second times the angle between them. And here we are dealing with this 90-degree angle between omega and R. So sine of that angle is also 1. And you end up with the same magnitude. And that is the vector you're looking for. Omega cross R. Very compact, very useful. In fact, a lot more useful than this form. You can immediately find the direction and magnitude of your velocity vector. Let me see if there is anything else. Yeah, obviously a couple of remarks. Now that we know V is omega cross R, change your focus. Note that V norm of V becomes R omega, given the angle between these two vectors are perpendicular. And the direction is given by right hand rule. So curl your fingers around the direction of rotation. Well, no, actually not. Point your what do you need to do? Yeah, keep your thumb around. Oh, no, that's not good. Yeah, right hand rule, basically. Yeah, it doesn't work very well with curling. With curling, let me see. Yeah, it doesn't work very well with curling. But your fingers start with pointing your fingers toward omega, then curl them toward R. Your thumb will give the direction of velocity. But it is a lot easier to note that if your body is rotating in one way, velocity has to kind of follow that. And also note that this is a reminder, omega cross R is not equals R cross omega. So be mindful of the order. And yeah, that is now all I wanted to say. So the only thing that remains is the acceleration of point P, and we will do that in the next video. So I'll see you there.